inaendelea.
So I want to teach now. That's okay. So you can see that. Good afternoon, class. Welcome to our chemistry lesson today. Our topic today will be rates of reaction, and your presenter is Madam Jennifer Gishohe. So we have had an experience of many reactions from the time we started learning chemistry, and this time round we would want to understand how a chemical reaction takes place and the factors that may affect any chemical reaction. So in our lesson today, we would want to start by asking ourselves, what is rate of reaction? And in short, the rate of a reaction is a measure of how much or how fast or slow a reaction takes place. The rate of reaction can be measured in two ways. And one of the ways is by checking on the rate at which the reactants are consumed per unit time. The other one is checking on the rate at which the products are formed per unit time. So in every chemical reaction, we'll always have reactants and products. The products will start at zero because at the beginning, we are only having reactants alone. So as the reaction proceeds, we note that our products will continue increasing. But the reactants at the beginning of a reaction are always at 100%. So as the reaction proceeds, then we note that the reactants will continue decreasing. And that is where we are saying we can measure the rate of a reaction by checking the rate at which the reactants are consumed, or we can check the rate of reaction by the measure of how the products are formed per unit time. So in short, we are saying that the rate of a reaction is a measure of how much of a reactant is consumed and how much of the product is formed per unit time. I hope it is clear on what the rate of a reaction is and how we can measure the rate of a reaction. So I'm going to show you a video that is going to illustrate more on the rate of reaction. So watch the video, enjoy yourselves. So did you enjoy the video? I believe you did. And from that video, I would want you to answer the following questions. 1, I would want you to identify the apparatus that can be used to measure the rate of reaction. In a minute, identify those apparatus that you have seen in the video that may be used during the measurement of rate of reaction. Now, I would want you to find out whether you have gotten these apparatus, and one of them is a stopwatch. In order for you to measure the rate of a reaction, we are saying that we are measuring it per unit time. Therefore, we must have either a stopwatch, a stop clock, or even a watch, a wristwatch. With those ones, you'll be able to measure. Number 2, you have noted that there is a weighing machine, meaning that if you want to measure the rate of a reaction and you are checking at the way the mass is decreasing, you may use a weighing machine to measure the masses. The other one that you have noted is that there was a syringe, that is another apparatus. And a syringe will be used to measure the volume of the gases as it is being produced. So in the example that we have just seen in the video, we noted that there was the carbonate and we were measuring the masses using the weighing machine. So it is expected that the masses were decreasing over time. And then we're also using a silage to measure the volume of the carbon dioxide that was being produced. So I believe you are able to see that the volume of the gas was increasing over a period of time, or as the reaction was progressing. The other apparatus are the common apparatus that we normally use in the laboratory, like you have the beakers, you have the conical flask, and so on. But of importance, in all the experiments, there must be a stopwatch. Now, it is very important for us to note that this is an area where the examiner normally bring a question at the council level, where they ask a student to draw the apparatus that may be used to measure a gas like hydrogen gas when magnesium is reactant with hydrochloric acid. Now, I want us to proceed with the lesson, and I would want to say this, that from what we have observed, we note that we drew 2 graphs. One of the graphs was that of the reactant, which was starting up high there. It was showing that we had a very high concentration of the reactant. It was at 100%, but you noted that it went on decreasing as time went on. Then there was another graph that was showing the products, which are starting at 0, because at the beginning we did not have any product, and they continue increasing over a period of time. So in a nutshell, we want to say at the beginning, the reactants are at 100% or the product at 0%. And therefore, we need to note that the graph of the product against of concentration against the time for the product will always start at the origin, while that of the reactant will start at the top as it moves down. There was a question from the graph. I have already given you the answer because of time, but as we move on, we continue learning more from the graph. Now that we have understood how we measure the rate of a reaction, then we need to ask ourselves, how do a reaction take place? How does a reaction take place? Inside that beaker, inside that flask, exactly what happens? And I want you to note that for any reaction to take place, the reactants must collide. I also want you to note that not all collisions between the reactants will result into products. Therefore, it means there are other things that must be done by these particular reactants in order for them to give the product. And what there is that the reacting particles must collide, and they must collide in the right orientation, and they must have a minimum amount of energy for them to produce any product. Now, the minimum amount of energy that the reactants must have in order for them to give a successful corrosion or an effective corrosion or an effective corrosion, you can use either of those terms, is known as activation energy. So we are saying that a successful corrosion or an effective corrosion is the one that will result into products. Now, we have already talked about activation energy, the minimum amount of energy that the reactants require in order for them to give us a product. And then below there are energy level diagrams. We studied this under energy changes in physical and chemical processes. But you note that this energy is a little bit more decorated. It is having, from where we have the reactants, there is a curve that is moving up to a hill up there, and then it starts going down where we are now getting the products. Now, the first graph is a graph that is showing the reactant, the energy of the reactants being lower than the energy of the product, meaning that during the reaction, energy was being absorbed from the environment. And therefore, this is an endothermic reaction. Now, you note that the curve is moving from the reactant, the level of the reactant, it is going all the way up, and it is making a hill. Now, the distance from where we have got the top of the hill, that energy from the top of the hill, you can see it is well extrapolated up to where we have the reactants. That is the energy that is known as the activation energy. If you get the difference from where we have the hill of the top of the hill, where the extrapolation is, that energy there, up to the energy of the reactant, you subtract that, you get the so-called the activation energy. You also note that the energy change does not change. It is that energy change between the energy of the product and the energy of the reactant. That is, if you get the difference between the energy of the product and the energy of the reactant, you will be able now to get the energy change, and it is clearly written on the graph there. The second graph is a graph that is showing that the energy of the reactant is more than the energy of the product. In that case, we are able to see that that reaction was losing heat energy to the environment, and therefore it is an exothermic reaction. Again, in this reaction, you note that the activation energy is also shown, where we have that curve that is moving all the way to the top there, and then down to give the product. The energy from the hilltop to the energy of the reactant, again, is the activation energy of that particular reaction. I hope the concept of the activation energy is clear, and I believe sorry for that. I wanted to say that I hope the concept of the activation energy is clear, and we will continue discussing the same, so that in our energy level diagrams now, we shall be including the activation energy. We would now want to know, what is this that we look at when we want to measure the rate of a reaction? What are these properties, or what are these characteristics that we should look at in order for us to be able to measure the rate of a reaction? And I wanted to say that from the apparatus we noted there above in our video, We had already seen that there was a weighing machine, and the weighing machine is supposed to measure masses. So the change in masses is one of the items that we may use as a property or a character that would help us to measure the rate of a reaction. The other item that we had noted was the silage. And the silage, again, would be used to measure the volume of gases. So you note that the change in the volume of gases will also enable us to measure the rate of reaction. The last one, which we did not observe in our reaction, is where we may have reactions involving color changes, where if the reactants were current, because as the reaction proceeds, they are decreasing, then the intensity of the color would decrease. On the other hand, if the products are the ones that are current, then we would note that as the reaction proceeds, then the intensity of the color is going to increase. Now, having understood the rate of the reaction and how the reaction takes place and the properties or the characteristics to check on for us to be able to do this, then we need to ask ourselves a question. Is this topic necessary? Do we really need to study the rate of a reaction? Does it have any application in real life experiences? And the answer is yes. So just a few examples will help us to understand that the topic is important and that we need to give it the seriousness that it deserves in order for us to be able to understand it well. So one of them is then that the knowledge of the rate of the reaction is applied in many disciplines, such as the industrial processes. We have covered industrial processes all the way from Form 1, where we did the fractional distillation, in Form 2, where we did the Sauvé process, in Form 3, where we did the Haber process, we did the Ostwald process, we also did the contact process. I want to believe that at this level now, those processes are in your fingertips. Now, in certain processes, like the Haber process or the contact process, the knowledge of rate of reaction is going to be very important because it is going to help us to understand the conditions that are suitable for us to maximize the production of the ammonia or the sulfur 4 oxide, which will result into sulfuric 6 acid, and how to minimize the cost of production and the dangers that may be involved in this. The second area that is of importance is the area of medicine. And in this case, it is important for a doctor to know how much time a particular drug, because drugs are chemicals, will take in your body before it is completely decomposed. So once the doctor knows the amount of time that the chemical will take in your body to fully decompose, then he will be able to give you a prescription. For example, he'll be able to tell you, take this drug 1 times 3, this tablet 1 times 3. That means that you are supposed to take that drug 8 hourly. After every 8 hours, 1 tablet is completely decomposed, and so you need another tablet. If it tells you, take this tablet 1 times 1, it means that this particular tablet takes 24 hours in the body before it is completely decomposed. The other area which is very important is the area on engineering, and particularly where the engineers will design machines. These machines are supposed to use fuel. So the engineer requires to know the rate of combustion of the various fuels. For example, there are those engines that will use petrol. There are those engines that will use diesel. Those engines are not the same. I hope up to that far we are okay. We understand why the engineer needs to know about the rate of combustion of a fuel so that they are able to design that particular engine. Last and not least, we have the food industry, where we have baking taking place. And this particular person who is baking requires to know the amount of time that a cake would stay in the oven, and also the temperatures that are required for the cake to completely bake. Otherwise, they would give products that are not fully baked. Yes. So I would want us to move on to the statement of the cohesion theory now. And we shall look at the statement of the cohesion theory. And from there, we shall look at also the factors that affect the rate of a reaction. And we have already talked about how a reaction takes place. We have talked about the reactants colliding in the light orientation and with a minimum amount of energy, which we have called activation energy. And therefore now, what is this cohesion theory all about? And the cohesion theory talks about the relationship between the rate of a chemical reaction and the number of successful cohesions. And it says that the rate of a chemical reaction is proportional to the number of the successful or effective cohesions between the reacting particles. Meaning that if the number of the successful cohesions are very many, then the rate of the reaction will be very high. If the number of the successful cohesions decreases, then the rate of the reaction also decreases. Therefore, they are directly proportional. So you cannot be able to explain the issue of the rate of a reaction without talking about the successful cohesions. Now, there are some factors that may cause an increase in the number of effective cohesion. That means any factor that will cause an increase in the number of the effective cohesion will therefore increase the rate of the chemical reaction. Why? Because the number of the effective cohesions are directly proportional to the rate of the chemical reaction. And now this one takes us now to the factors that affect the rate of a chemical reaction. I would just want to mention them, and then we shall look at them one at a time as we also perform some experiments. And the first one is concentration. How does concentration, changing concentration, affect the rate of the reaction? The second one is temperature. We are having a reaction. We are having a reaction going on. How would varying the temperatures of this reaction affect the rate of the reaction? We also have surface area. And in this situation, we should ask ourselves, we are having a reaction. Maybe it is involving a solid like the calcium carbonate. How would changing the surface area of the calcium carbonate, maybe by grinding so that we use powder instead of granules, affect the rate of the reaction? We also have catalyst as a factor. And we note that there are some reactions where we normally use catalyst. So how does this catalyst affect this reaction? We also have pressure also as a factor. And again, we would want to ask ourselves how pressure will affect the rate of the reaction. And finally, we have light also as a factor that affects the rate of a chemical reaction. So we are going now to look at these factors that affect the rate of a chemical reaction one at a time. And we are going to start with the first one, which is the concentration, where we are going to see how we can perform an experiment. And from there, we move on with our discussion. So we have concentration as a factor, and we want to see what is the effect of change on concentration on reaction rate. So we have an experiment that we are going to perform, and the experiment is where we are going to consider the reaction between hydrochloric acid and sodium thiosulfate, whose formula is Na2S2O3. Sorry, it is sodium thiosulfate, not 8. Sulfite, not sulfate. We have a procedure that has been provided for us. We are going to measure 200 cubic centimeters of distilled water. We'll put it in 4 separate conical flasks. And we shall label them as 1, 2, 3, and 4, respectively. Now, to the first flask labeled 1, we are going to add 0.5 grams of sodium thiosulfate, which is provided for you, and we are going to stir until it dissolves. Then we shall take that flask in our next step, place it on a plain paper with a cloth on it. You can use a pencil to write a cloth on a piece of paper. And then you place your content, that is the solution of sodium thiosulfate, on top of the paper where the cloth is. Now, you're going to notice that because the solution of sodium thiosulfate is colorless, from the top of the flask, you'll be able to clearly see the cloth. The next step is where now we are going to add 5 cubic centimeters of 2 molar hydrochloric acid to this particular flask. And immediately start the stopwatch to measure the amount of time taken for the cloth to disappear. I would want to explain just a little before we move on to the other experiments, that during the reaction between hydrochloric acid and sodium thiosulfate, one of the products we get is sulfur, and sulfur is a yellow solid. So as the reaction proceeds, the sulfur is produced. And when the sulfur is produced, it continues covering the cloth on the paper. And that is why at some point we no longer can see the cloth. So we are going to measure the time at which enough sulfur is produced just to cover the cloth so that we can no longer see it. In our next procedure, we are going to repeat the experiment we have just done above, but this time with flask 2, we are going to add 1 gram of sodium thiosulfate instead of the 0.5 grams that we did in flask 1. We place it again on the cloth, and we add 5 cubic centimeters of hydrochloric acid and start our stopwatch. We repeat the same with flask 3, where this time we are going to put 1.5 grams of the sodium thiosulfate in the water in flask 3. And then we are going to place it on the cloth. We add the 5 cubic centimeters of 2 molar hydrochloric acid, and then we start the stopwatch and we measure the amount of time taken. And finally, we are going to repeat the same experiment with flask number 4, where we are going to add 2 grams now. We place it on the cloth. We add the 5 centimeters cubed of 2 molar HCl, and then we start the stopwatch just to note the amount of time that is taken for the cloth to disappear. You take the shortest time possible to do that experiment so that we move to the next level. So below is a table that I want you to fill. And the table has clearly shown you the masses of the sodium thiosulfide, 0.5, 1.0, 1.5, and 2.0 grams. It has given you a column where you are now supposed to calculate the concentration of the sodium thiosulfide in grams per dm cubed. And it has given you a column where you'll be filling the time that was taken for the cloth to disappear. After you have done that table, you'll move to the next level where I want you to discuss and answer the questions that follows. Question number 1. In which flask was the reaction fastest? In which flask was the reaction slowest? Explain your answers. Number 2, you're supposed to plot a graph of concentration, that is the y-axis, against time, which is on the x-axis. Number 3, what aspect of the reaction is observed in measuring the rate of reaction in the experiment above? Discuss amongst yourselves. Number 4, I would want you to plot a graph of now concentration against 1/time per second. Finally, number 5, how does the concentration affect the rate of a chemical reaction? So you do the experiment, you ensure you are quick enough to finish the experiment, make all the possible observations, and then sit down and discuss the questions that I have already plotted. Now, for question number 4, I would wish that on that table that I gave you above, that is that table, I would want you to add on that column that is not written anything, 1/time. You get 1/time. You already have time, and the time should be in seconds. Now in the next column, I want you to add up there 1/time, so that you are going to use that 1/time and the concentration that you have calculated there to obtain the next graph, which is concentration against 1/time in question number 4. And once you have done that, I know you are going to enjoy the work that you are doing, and we are going to discuss that practical and the questions that you have in our next lesson. And until then, goodbye.